You know those chaotic squiggles on a stock chart? Or the sound wave of your own voice? What if I told you they both share a secret, a hidden symmetry? We're going to uncover a simple mathematical rule that lets us find a perfect hidden order in just about any signal you can imagine. So much of our world, right? It's just signals that look like a total tangled mess. But what's so cool is that hidden inside all that chaos is a really basic structure. And today, we're going to learn how to untangle any signal, seriously, no matter how complicated, and show that it's really just two super simple, predictable shapes added together. That's it. That's the big idea. Okay, so let's start with the first of our two simple shapes. This is what we call an even function. The easiest way to think about it, it's a perfect mirror image right down the middle across that vertical y-axis. You know, whatever happens on the right side is exactly what's happening on the left. The classic example is a parabola, you know, that U shape, or a cosine wave. And the math behind it is just as simple. The value of the function at, say, -2 is exactly the same as its value at +2. All right, now for the other half of the pair, the odd function. This one has a totally different kind of symmetry. It's not a mirror image. Instead, it has what we call rotational symmetry. Picture this. If you take the graph and spin it 180 degrees around the very center, the origin, boom, it lands perfectly back on itself. A sine wave is a great example, or the function x cubed. And the rule for this one, the value at -x is the negative of the value at +x. Okay, but here's where you might be thinking, hold on a second. These perfectly symmetrical shapes, they seem kind of rare in the real world, don't they? I mean, most of the stuff we actually see and measure just doesn't fit neatly into either the even or odd box. Yeah, just think about it. The sound of someone talking, data from an earthquake, that stock market chart we mentioned, they all just look kind of random and messy. Definitely not symmetrical. So you're probably wondering, what's the point? Why are we even talking about these perfect even and odd functions if they don't seem to apply to most of the things we actually want to analyze? Well, this is the magic trick. This is the secret superpower of signal analysis. It turns out that any signal, and I mean any signal, no matter how messy it looks, can be perfectly rebuilt by just adding one purely even piece and one purely odd piece together. So this isn't just about labeling a few special functions. Nope, it's a universal tool we can use to take anything apart. So how do we actually do it? How do we pull off this magic trick? Well, it all comes down to these two formulas, which are actually way simpler than they look. Think of them like a prism for signals. To get the even part, all you do is take your signal, add a time reversed, a flipped version of itself, and then just divide by 2. To get the odd part, you do the exact same thing, but you subtract the flipped version. That's literally it. It's a foolproof recipe for finding the hidden, symmetric parts of anything. And here's a really important detail. This decomposition is unique. That means for any signal you can think of, there is only one right answer for the even part and one right answer for the odd part. This isn't some guess. It's not one of many possible ways to do it. It is the way. And that certainty, well, that's what makes this whole thing so incredibly reliable and powerful for engineers. Okay, let's make this real. Take a look at this example. This function here, it's basically a wave that's dying out over time. And as you can see, it's definitely not symmetric. But when we plug it into those two formulas we just saw, look what we get. We get these two totally separate components. The even part, which you can see is perfectly symmetrical, is described by something called a hyperbolic cosine. And the odd part with that cool rotational symmetry uses a hyperbolic sine. Now don't get bogged down by the names or the math. The only thing you need to know is that if you graphed these two new pieces and added them up, you would get the original messy signal back perfectly. All right, so we've got this cool math trick. We can split any signal. But so what? Why did I call it a superpower? What's the actual practical payoff here for scientists and engineers? Well, the answer comes down to a classic strategy: divide and conquer. And this quote really nails it. You see, in digital signal processing, or DSP, which is the tech that makes your phone's mic work, that makes satellite communication possible, all that stuff, the main strategy is something called superposition. Now that sounds fancy, but it's a really simple idea. It just means you take a massive, complicated problem, you break it into much smaller, easier to solve pieces, you solve each of those little pieces, and then you just add all those simple solutions back together to get the answer to the original huge problem. And that is exactly what this even and odd trick lets us do. We're splitting a messy, complicated signal into its clean, simple, even, and odd parts. We've literally replaced one hard problem with two way simpler ones. And it just so happens that the perfect symmetry of these new parts makes all the math that comes next so much easier to handle. Now here's maybe the biggest payoff of all. One of the most critical tools in all of engineering is the Fourier transform. It's what lets us see all the different frequencies, like the bass and the treble, that are mixed together inside a signal. Now, usually the math for this involves what are called complex numbers, which have a real part and an imaginary part. It can get, well, complex. But check this out. When we do a Fourier transform on our symmetric pieces, something amazing happens. For the even part, the answer is purely real. The imaginary part just disappears. And for the odd part, the answer is purely imaginary. This basically cuts the amount of work our computers have to do in half. It makes everything faster and way more efficient. So this really shows you the everyday workflow. An engineer gets some complex signal. Step 1, they split it into its even and odd parts using those simple formulas. Step 2, they run their analysis, whatever it is, on those two much simpler parts separately. And then step 3, they just add the two results back together to get the final correct answer for the original messy signal. It's such an elegant and incredibly powerful shortcut. So what have we really learned here? We found that underneath the surface of pretty much any chaotic-looking signal, there's a simple, symmetric foundation. It's proof that really complex behavior can come from combining a couple of very simple rules. And, it kind of makes you wonder, what other beautiful, simple principles are just hiding out there in plain sight, just waiting for us to find them, to help us understand the complex world all around us?